Yeah, thanks. So I'm Karim Essafi working at Kinesis. So I'm going to tell you about quantum chemistry algorithms for on quantum computers that go beyond VQE. So just for a little recap, so Kinesis is a quantum computing startup based in Tokyo in Japan. So it was founded in 2018 by our CEO Tenin Yan. And we have some advisors at the Osaka University, including Professor Keisuke Fuji, who is a big professor in quantum information. We have about 50 employees, with half of them having a PhD either in physics or in chemistry. And we develop algorithms and software for quantum chemistry using quantum computers. So our focus today is going to be on quantum chemistry. So just as a small recap, so in quantum chemistry, the wave functions contains all the information about the electrons of a given molecule. This information can be used to compute the different properties of the molecules, such as energy or the structure or the reactivity. However, this computation can be very challenging because of the complexity of the electron structure. Even if the molecules can seem small, like it's still very complex problems. And we can solve some of them using quantum computers if the molecule is small, but as soon as we get bigger and bigger molecules, that becomes very challenging both for classical computation and for quantum. So the algorithm that's been used a lot in quantum computers is the variation quantum eigensolver. So this is a hybrid quantum classical algorithm for minimizing the expectation values of some parameterized circuits. And here you have a schematic view of how this algorithm works. So first you define your fermionic Hamiltonian and your Hartree-Fock wave function. Then you map this into qubits. And then you find an ansatz that you want to minimize with some parameters theta. And then you send this to your quantum computer where you do the preparation of the trial states, and then you do some measurements. You feed that measurement to your classical computer for the optimization, and then you feed back the results back to the quantum computers, and you go back and forth like this until you reach some converged results that minimizes the ground state energy, for example. So the applications of VQE are quite wide, going from you can use to do molecular dynamics, photochemistry, but also for solid state materials as well to calculate, for example, the band structures of a given material. However, the issue with VQE is that it requires a lot of resources in terms of number of qubits to deal with the noisy circuits that we have. And the problem is that the current hardware has the quantum computing resources are very scarce, meaning that we have a low number of qubits and the gate fidelity is still relatively low to be able to do VQE for large molecules. So one would need to find techniques that reduces the required number of resources. And that means like reducing the number of qubits, having shallower circuit depths, while still having a high performance so we can tackle more challenging problems. So how do we reduce this? We can either develop a more efficient algorithm that requires fewer resources to reach the chemical accuracy. We can use symmetries of the systems at hand. And we can also use some quantum embedding methods, for example, where we divide the system into two parts, where it's one high level and one low level method, depending on the part that we are tackling. So at Kinesis, we focus a lot on research. And in our research, we have developed different ways of either improving VQE algorithms or going beyond VQE, which we're going to be talking about today. And also, we also have some stuff on fault-tolerant quantum computing. So today I'm going to mainly be talking about grouping via finite projective planes and the quantum selective configuration interaction, or QSCI for short, and an adaptive version of it called adapt QSCI. So this at QSCI, we published or we submitted papers to arXiv last year. And the idea behind this is that the ground state energy on a noisy device can sometimes not, like the results that we get using VQE can sometimes not be variational. What I mean by this is that even if the VQE is technically a variational algorithm, it means that it should respect the variational principle. In practice, when you run this on an actual device, you have either statistical noise or physical noise on the device that can lead to measurement errors, and those measurement errors can lead that you violate the variation principle, which means that you can find ground state energies that are actually lower than the real exact energy that you would get if you knew how to do the exact computations. And you can see this already in this graph here, where some of these stars are below the exact value, which is the red lines. So to overcome this challenge, we want to develop an algorithm where a low value of the energy still respects the variational principle, and at the same time reduce the quantum resources required to do this. And this is where QSCI comes into play. So here we have an overview of how this algorithm works. So we start with some input states, which is called psi in. And then we measure the states in the computational basis on a quantum computer. And then we do a sampling, which means that we're going to select the configurations that appear the most. And then using these configurations, we're going to reconstruct our Hamiltonian or classical computer in a subspace, and then diagonalize this Hamiltonian in that subspace. And by doing this diagonalization is done classically, so it doesn't require any more quantum resources besides the sampling phase. And on top of that, the ground state energy that you would get, because it's an exact diagonalization on a classical computer, you don't have the hardware noise that comes from quantum devices. And also, we know how to do exact diagonalizations for quite large systems on a classical computer. And by doing that, the energy that you would get will be exactly that subspace, and you will obey the variation principle. And I'll show you some of these results. So here is QSCI, where we start with VQE as our input states. We have run this simulation on a noiseless simulator, and this was done for a water molecule using 10 qubits. And looking at the different results, so the colors correspond to different sizes of the subspace. So R defines how many configurations we have selected for our subspace. And you can see that already at R16, which is this orange line, we are already at the chemical accuracy. So here, the y-axis corresponds to the energy difference between the one we get from QSCI or VQE minus the exact energy that we would get using CASCI or FCI. And you can see that QSCI with a subspace equal to 16 has already reached chemical accuracy, and it gives us results that are lower than what you get for using VQE. And for comparison, using a classical method, if you use a CASCI for this problem, you would need about 100 Slater determinants. So this is doing exactionization on a subspace of R equals 16 is actually easier and faster to do than you have to do our CASCI calculations. So you can see that this is already showing some promising results. And then we also run this on a linear chain, H4 molecule using 8 qubits. And this was run on the INQ device. So this was run directly on a noisy computer. And the different lines that you see on the graph corresponds to the different iterations. The color corresponds to the size of the subspace. So yellow is R equal 1 and orange is the same as before, R equals 16. And the lines with a marker corresponds to an average of different runs at that subspace size. And one interesting fact you can see here is that some of the runs actually perform better than using CISD, which is the configuration interaction with the single and double excitations. So some of these can have better accuracy than on a classical computer. And in general, if we take the averages, we get better performance than doing VQE, for example. And which means that we could get higher accuracy using fewer iterations than we do using VQE calculations. And to see how this method, if this is scalable, because we're interested in larger molecules, so we did simulations to extrapolate what this would look like if we had access to 50 qubits. And we tested this on the CR2 molecule with varying different sizes of active space. So here we have we look at the resources both on the classical and the quantum side. So on the classical side, this is not very demanding, so the scalability will be just fine. And you can see that if we wanted to run this problem for 50 qubits, we would need about 10 to the power 3, which is like 1,000 Rs, which is thousands like size of our subspace. And we know that this is not a problem because we can run up to 10 to the power 7 on a supercomputer. And looking at on the quantum resources required, basically, if we had access to a 50 qubit device, we could do all the sampling within 1 day for this specific molecule. So you could say like in about 2 days, you could get very good results between doing the sampling and then doing the exact diagonalization on a classical computer. So in summary, this method is very promising because one, it obeys variation principle, requires fewer resources than the standard VQE, and also you can run this with shallower circuits. But of course, at this level, we were still using VQE as our input state. So future direction will be to use a different method for the state preparation, and also to apply this to test this on bigger molecules to have a better demonstration of the quantum advantage that you would get from this approach. So this first thing is what we have already done, and that's my next couple of slides are going to be about adapt QSCI and how this works. So this was also published last year. So the idea of adapt QSCI is to use an adaptive construction of the input states in which that we run the QSCI algorithms multiple times and we grow the input state iteratively. So this is a similar idea to adapt VQE, for those who know adapt VQE, and I will tell you a little bit about what's the key advantages of adapt QSCI compared to adapt VQE. So at the first step, you define a pool of operators that are the generators of rotation gates, and you put this in a pool, and then you also choose initial input states. An example of these operators could be a single or double excitations of electrons. So this is the similar things that you would do if you're using adapt VQE. And then you perform a QSCI on the input states that you have chosen at the step K. This will generate your R-dimensional subspace, then which you use to construct the effective Hamiltonian, and the smallest eigenvalue and the associated eigenvectors are EK and CK. And then you use this CK to do an evaluation of this quantity H, which is basically the expectation value of the commutator of the Hamiltonian with these operators P. And then you choose the operator in the pool with the largest value of H, so in absolute values, and you denote it as PTK. And then you use that operator to construct the next step, step of your input state, and with some parameter theta k. And you minimize this function here to find the optimal value of theta k that we denote as theta star, and then we inject that into the input state phi k plus 1, so at step k plus 1. And as I was saying, the theta star is the one that we get from this minimization here. So your new input state is the one given here. And there's several key advantages of doing this. So one advantage is that you only need a quantum computer for step 2, so to perform the QSCI generation of the R-dimensional subspace. You need fewer number of measurements compared to adapt VQE, which means that you would require fewer quantum resources. And the parameters theta do not change from one iteration to the next. So which means that if I find my theta star 0, then when I move to step k equal 1, that value of theta star 0 remains the same, and I just need to optimize to find theta 1, the optimized value of theta 1. Whereas in adapt VQE, at each step, you have to re-optimize all the parameters, which makes it much more resource intensive and time consuming as well. So here are some of the results comparing adapt QSCI and adapt VQE. And what we have seen is that, so this was run on our H4 and H6 chains. And we see that we require fewer C0 gates to create our state phi k, and to get a more accurate results than we would need than we get if you're using adapt VQE. And you can see this in this graph where the blue dots correspond to what we get from adapt QSCI, whereas the red line is the one from adapt VQE. And you see that you need more numbers of C0 gates for both systems. And if you look at the number of shots, we see that adapt QSCI was requiring 10 to the power 6 for H4 and 10 to the power 8 for H6 to reach chemical accuracy, whereas for VQE, the lowest number of shots that you would need to get to reach chemical accuracy as well is a magnitude bigger for H4 and like 2 to 3 times bigger for H6. And this is like basically a lower bound. So the actual resource number of shots that you require is actually much bigger for adapt VQE than you would get from adapt QSCI. So this is a very promising method to use for NISQ devices that would allow us to tackle bigger molecules. And on top of that, the next direction that we need to do is to extend this algorithm to excited states calculations. And I think I still have 1 more minute or two, I guess. So I might jump over this part and just tell you directly about the software we've been working on, Curie and CurieParse, and I'm just going to be talking about CurieParse here because I think it's more relevant for QHAG. So this is a Python library that we developed that is very modular, which means that you can use the modules that we have it and combine it with your own algorithms or your own modules that come from either other libraries. And you can run it on different platforms, either on a simulator using QLAX or STIM, or also on real devices via Amazon Braket or IBM Qiskit. And there was a lot of focus on high performance. And here we compare CurieParse in orange with PitCat and PennyLane, and you see that at least for small number of qubits, CurieParse is performing better, and they basically perform similar at when the number of qubits increases. And if you want to test this library, we have some ready-made tutorials that you can access going to this link. And we have different types of tutorials, either to estimate expectation values, doing sampling, you having noisy simulations, or even error mitigations and other stuff that you can have look into. So thank you for your attention. And if you want to reach me, you can either reach me on the Discord channel or via my email. And here's a QR code where you can access all of our papers at Kinesis. Thank you.
All right, Karim, thank you so much. I'll leave this slide up here for those who want to see your email and scan that QR code. Yeah, thanks so much. That was super interesting, actually.
Thank you.
Let's get into some questions. We actually do have quite a few here. So we have Chengling_X0 on our Twitch asking, is QSCI outperforming classical select CI?
Good question. Is it outperforming it? So at least at the level we have now, we show that it has similar performance, at least for smaller molecules. Let's see. I don't have so here, of course, we only can test this because we don't have access to bigger quantum computers. For these small molecules, it has similar performance, but with fewer number of resources. I was saying that, so CASCI is a classical CI, and you see that for this one, you would be diagnosing a system with 100 slated determinants, whereas using QSCI, you can do this with 16, basically, dimensional matrix. 16 I would say states in your subspace.
Okay. All right. Okay. So Chengling, hopefully that answers your question.
And here it compares also with CISD, which is also another configuration interaction with single double, which is also a classical method for this. So.
All right. Okay. Nice. A question from Kentucky Kirby on one of your slides. I can't remember which one. There was you showed some results for Chromium 2. Kentucky Kirby just said Chromium 2, interesting choice. Why?
Oh, because this was like a complex molecule to work on. That was complex enough that it was interesting, and small enough that that would be like a goal of medium term goal to be able to do this one, and was a very, I would say, in some ways trivial one to make the resource estimation for in a easy and clear way.
Right. Okay. One last question here from Andresulid. I'm not entirely clear on the role of a quantum computer in implementing the method utilized by QSCI. Generally, is this computation carried out classically?
It's both. It's a hybrid algorithm. So you here at the input state. So this part is quantum computer, and this part is classical computer. So what you do in the quantum computer, you do the sampling. So you prepare your input state, you do a sampling. The sampling will tell you, when you do sampling, you have such a number of configurations that will appear, and you will select those that appear the most. And those that appear the most, you use afterwards on a classical computer. You feed that to a classical computer to construct your subspace and do your effective Hamiltonian diagonalization over there.
Right. Okay. All right. Well, there was a couple more questions, but if you want to ask them on the Discord, that's the place to do it now. For now, we have to say goodbye. Thank you so much, Karim. Karim, this is your second Q hack, or is it your third?
Yeah, nice. Second.
Second. Right. Okay. So Karim's, I think actually, Karim, your previous Q hack talk is on the Xanadu YouTube channel. So if you guys do want to go check that out, a throwback to last year, this one will be up on the PennyLane YouTube channel right when the stream ends. So if you want to watch that back, you can. All these are being recorded. They're all on our live, or they're all being recorded live right onto our YouTube channel. So yeah, watch them back at your leisure. Karim, it was a pleasure to have you again at QHack. Hopefully we can have you back next year. Have a great rest of your day.
I hope so too. Thanks, Isaac.
All right, cheers.
Have a nice day.